hear me well? Yeah,
I hear you good. Hey
cool.
everyone, it's Andrew Brown, and welcome to another video. I have Rola, who is definitely an expert comparative to me, which I know nothing, as you just heard me talking about BERT. But let's see if we can actually find out really how BERT works. And so I have my slides pulled up here. Let's bring them up here, and Rola is going to help us enrich the information I have. So when I learned about BERT, I actually learned about it in the machine learning AWS certification. I didn't think much of it because I thought it was old and maybe folks don't use it anymore. But I was at an event with Rola at the AWS Montreal user group, and I heard her say there are use cases where you can still use BERT or should use BERT where LLMs might be too much work. And so I wanted to kind of dig a little bit more into that. And so I have my slides up for display here for Rola. And so I understand BERT to be this bidirectional encoder representation from transformers. It was researched by Google. And, I saw a video which showed the transformer architecture. And what they did is they just split it in half and took the first part of the architecture and stacked it. And they called that BERT. So is that true? Is it just cut in half and then stacked?
Well, so transformers come. They have two pieces, right? They've got the encoder piece, which encodes data. So it takes natural language and encodes it into mathematical representation. And then you've got a decoder, where if you've got mathematical representation, you can pass it through a decoder and get natural language, right? And the first generation, I think, of LLMs came as an encoder decoder couple. And so you would put in natural language, it goes through this mathematical system, and then you would still get language out of it. Exactly that. So there's a encoder decoder. GPTs, for example, are a decoder only, but BERT itself is an encoder only model. And so what that means is you have to think of these things as what is the input and what is the output. And so an encoder only model takes in natural language, or takes in, in our case, in a language model, it takes natural language, and then it comes out with a mathematical representation, right? And so what BERT is, and then you add a few layers of, these things are neural nets at the heart of them, and so you add a few layers, and you can come up with different representations. And so what BERT is really good at is things like sentiment analysis, for example, or classification. So you think of it as input is text, a lot of text, and output is less text. So either a word or a sentiment, a classification, something like that. Does that make sense?
Yeah, and one thing that I think I got from that as well is that you were saying that BERT, if we go back here to the architectural diagram, and I just want to confirm if this is what I understood. I'm trying to get one of these images a little bit larger here. It's a little bit hard today. I'm not sure why it's making it hard for me, but I want to go back to that transformer architecture. And I just want to make it a little bit larger if I can here. So just give me a moment here to get the link. So I'm just copying the link address here. And so here is the transformer architecture. And you said, well, I said BERT's just this side stacked over onto itself, and that's what we get for BERT. But I think you had suggested that GPT is the right side that is stacked upon itself, or is it, if you just
GPT
took
or
the right side, would that be considered GPT?
Yeah, GPT are decoder only models. I mean, in a nutshell, yes, but yes. So uh, they're not encoder decoder. They're decoder only models.
Hmm. Okay, interesting. So let's go over into the next part of BERT. And so, yeah, so BERT is bidirectional, meaning it can read text both from left to right to left to understand the context of text. Sorry, yes?
That's not exactly what it means. It's supposed to be non. The naming is a misnomer. It's non-direct. It should be named non-directional. It's called
Mm-mm-mm.
bidirectional. The idea is that it doesn't. The sequence of words often matter, right? And so if you say, I don't know, A killed B or B killed A, it's a very different understanding of how
Mm-mm.
things are. And so traditionally, the way it worked is, we had RNNs and different variations of recurring neural networks, and the way they did that is through sequential understanding.
Mm-hmm.
The transformer architecture changes that, and attention changes that, in that that sequence is understood differently, not sequentially, and this is why the non-directionality comes in, I think.
Mm. Okay. So, all right. So that makes sense. So it's, oh, sorry.
It
Yes.
takes in all of the data at once. It doesn't read right to left nor right left to right. It just takes in all the data. Uh,
Mm-hmm.
but internally, it works in a mechanism where it is not reading through a sequence. It's really the attention mechanism make it so that it can highlight certain words in association to others.
Okay. So have you ever seen the movie? It's a comic book movie. Um, have you heard of Doctor Manhattan? Have you ever heard of Doctor Manhattan? So Doctor Manhattan is he's all knowing. Not like he becomes uh I don't know. He becomes like kind of like a god, and
Mhm.
he's aware of everything all at once at all times. So would we interpret its understanding as it contextually is aware of all the words in all directions? Would that be a better description, or?
I think it is aware of all of the words, but it is able to give certain words more importance based on what it understands of language. So there's a combination of things where where one word kind of enhances another, and it starts to pick up these nuances of word connections based on its own training. So it is aware of all of the words. It just understands which words it really needs to focus on, right?
Okay,
So
so
all of the articles, for example, doesn't necessarily care for. Does that make sense?
yeah, it's contextually aware. Okay,
It's
so
contextually
so
aware. It's
so
exactly
instead of,
that's the attention
I see,
mechanism.
I see.
It's
So
context.
instead of thinking of like it's reading left to right, just understand that it's contextually aware of each word and its importance in a sentence. Okay.
Exactly.
And the movie I was thinking of is called Watchmen. If anybody cares, I don't know why. I just I had to remember what the movie was. So BERT is a pre-trained model on the following tasks. So two things that it says it does is mass language modeling, so MLL, and the other one is next sentence prediction, NSP. So my thoughts is like you train the model based on these two things. Does that mean in its pre-trained state, like it's been trained for these two things, that that's all it can do at this point? Is like it can infer if you were to do these two tasks, it would be able to do it in this state. Because I was trying to figure out what can you do with this model. I assume you can't do anything with this model unless you train it again. But can you do anything with it in the non-trained state, or sorry, the pre-trained state?
I think there's a lot. So there's something called emergent tasks in LLMs where you train it for a specific thing, but it turns out it does this other thing really well, and we call that
Mm-hmm.
an emergent task.
Okay.
Um, and we're learning that the bigger the model size, then the more emergent tasks it has. So the fact that it is pre-trained on these things, then we know that it can do these things because it has been trained on them. But there has been a lot of emergent tasks and a lot of I think a lot of people were surprised at how much, for example, that GPTs can do in terms of solving different problems, and that's because of the size. Now, BERT is a model that is about 340 million, so it is a couple of orders of magnitude smaller than our bigger models. You have to remember this is one of the few first models that came in. The transformer architecture came out in 2017. This came out in 2018.
Mm-hmm.
Um, so it is one of the first models. It is one of the smaller models at 340 billion. The GPTs right now are about 1.2 trillion. So it's about a couple of order of magnitudes bigger. So I'm sure it can do more than that. I have to remember use cases. I have seen it. We have projects where we are running sentiment analysis and classification with BERT, but I'm sure there's other things that it can do. I just haven't played with it enough.
Okay. So that word emergent, do you say emergent models or
Emergent tasks or emergent,
emergent tasks?
it's things that
So
it can do.
again, to ground it to a real world example, I'm gonna keep doing this. As a real world example is like Ozempic was supposed to be for something else and now it's used for weight loss. Is that kind of like
Exactly.
okay?
Exactly. You discovered that it can do this, right? So
But was that the case with BERT? They like did not expect to you like, or was it like they made the transformer architecture and then they said, okay, we're gonna just take off the first half and see what we can do with it, and then they were They're like, oh, I guess I can do this, or well,
I think the first thing that I have to go back through the literature.
mhm.
Um, I think they were just experimenting with different models and things like that. I don't know that this is not the one with the sequence to sequence. I have to go back and see. Um,
Well, if you want, I have a pause feature. I can pause if you want.
yeah, let's pause
Let's
that.
pause.
Let's pause and see.
All right, we're back from pause land here, and so we did a bit more research in here, and I don't know if we remember exactly what we asked because we had a really good sidebar conversation. But I think we were talking about the discovery of BERT and what came before it, or like did GPT or BERT come first? I think that was it. BERT came first, or GPT came second.
So it depends on different references. We looked at two different references, and so like we said, the Transformer R paper, which is the Attention All You Need paper,
Hmm.
came out in 2017, and that was uh, a work between Google, but also the University of Toronto. I should say that as a Canadian. People forget that it's University of Toronto. It's a
Hmm.
and then there and in 2018, BERT came out as an encoder only model, and the GPTs came out also as a decoder only model. And based on my reference on the book I'm reading, it said that BERT came first. But when we looked on the internet, there were references that said GPT-1 came first. So I would say they came at the first in the same year. They're the first two, I guess, one of the first two that came out.
Well, that kind of makes sense because if they had this transformer architecture and then they split it in half and played around with it, I could see them doing that. I can't imagine that they made them in Iceland and then attached them, or maybe they did. I'm not sure, but all we know is that all these things happen close together, and we are where we are now. Um, but anyway, we'll continue on here. So BERT can be fine tuned to perform the following tasks. Now, I only know BERT for one thing, and that's to use it for embeddings. I shouldn't say that because I did run BERT a few times in this GenAI Essentials course for different fine tuning, but I did not realize how broadly it could be applied to things. So we had name entity recognition, question and answering, sentence pair task, summarization, feature extraction, embeddings, and more. I actually have another example. I can't remember what it is, but it's on the next slide. Um, and so there's all these things that you can do for fine tuning. What do you see folks using BERT the most for in the industry, or like today, like what would people gravitate towards BERT to utilize for?
So I see it I've seen it work with classification. So you give it a piece of text and then you classify that as a particular label you're interested in. And that makes sense. All of these things, if you think about what they are, named entity recognition, I see sentiment analysis as well. We some people use that, which is also a label in a sense. They're all the same type of work. So encoder only models are really good at analyzing text to reach a conclusion, right? To do some sort of task to reach a conclusion, not for to generate a sequence to sequence system. So yeah, this is all in line. And I think, yeah, the most I've seen is classification and sentiment analysis.
Okay, so classification, sentiment analysis, that's good because those are the two main, or sorry, embeddings, and then the other two, as you mentioned, were the ones that I were utilizing it for. I'm surprised it can do question and answering, but I always wonder if like the very early, oh, sorry, yes?
I think even if it does question and answering, it's fairly short. Like the
Mm-hmm.
the output context window would be fairly limited.
Well, this wouldn't be something that people would use as something for their website, say as a customer service bot. It would be too incapable of it.
Yeah, I don't think that's what it's made for. It's not I think the context would be fairly short.
Mm-mm. So there are multiple sizes of BERTs. We have 100 million parameters, 240 million parameters, 4 million parameters, and they said there was like 24 other varying models. I'm assuming BERT base uncased is the most used model. That's the one I keep seeing the most. I'm not as sure as to why, but obviously I would imagine that you're going to get different levels of performance based on the amount of uh, parameters being used. Is BERT tiny 4 million, is there any use case for such a small model, or other than learning?
I think if you can put it on edge or something like that, potentially. It depends again what you want to do with it and how well it does. So
Hmm.
you'd have to. It's really hard to know what a model will do in any particular situation. What we do know though is that. Sorry. What we do know is that so there's a really good paper that came out called the chinchilla paper. I don't know if you've
Mhm.
heard about that one.
Mm-mm. Nope.
Okay, so the chinchilla paper looks at optimizing model the model sizes versus the data versus the compute. So it looks at let me pull it actually let me pull it in. But some really cool things came out of that paper. Um, and the idea is that let me get you the name of that. And so it really looked at the relationship between the model size, the data set size, the compute resources required. And what it came out with it realized that obviously the bigger the model, the more information it can understand, the better, the more things it can do. But also the bigger the model, the more data it needs, right? So it came up with the idea that many models seem to be over
Mhm.
parameterized and under trained. So um, can we do a lot with 340 million? I think we can. Uh, it depends on what data it's seen and what data you use to give it. So yeah, you can if you fine
Okay.
tune it specifically
So
on what you
so
want it
sorry.
to do.
The one key thing that the one thing I heard that sounded very important was that there are models that are over parameterized but under trained, meaning that they have a lot of connections
Mhm.
between their nodes, but the amount of passes, I'm assuming that's when we mean training, is few, or the data plus passes going through is not enough.
Yeah, so there's a lot of space in that model to learn. It's like
Mm,
having a big brain, but not actually filling it with much in a sense, right?
mm,
Like
mm, mm,
so the idea of the size of the model, we have to understand. So is 340 million enough? Well, it depends on what data it's seen, right? So these things tend to be very difficult to judge like that. Um, and so it's a combination, and the bigger the model is, then the more data it should see for it to do a decent job. And so the chinchilla paper came out with the conclusion that a lot of models seem to be over parameterized and under trained. So they would get used. They would do better if they see more data. And just as a side note, I think they came up with the number that the data set size in tokens should be about 20 times the number of parameters. So if, for a 340 million parameter model, you'd have to multiply that by 20 to understand what the size of the data set that's ideal for that model.
okay. So I guess my other thought is that if you have a model that has a
Mhm.
lot of parameters, but you don't do many passes of training and your data set's not that large, is the size of the model going to be smaller because the training was less intense, and or the parameter size is going to basically determine the
The
size of the
param
model?
the parameter model, the parameter size, which is in a sense just how many parameters this model has, that's constant. So even before a model is trained at all, it still has the exact same parameter models. And
Hmm.
what ends up happening in the training world is those let's say 340 million parameters, they're initialized to random weights.
Hmm.
They're initialized randomly, and then as it sees the data, what it does is it makes a prediction, and then it goes back to, it we say it optimizes an objective function, so it estimates how off it is, and then it adjusts those parameters accordingly, and then it loops over and over. It makes a prediction, calculates its errors, readjusts, and then it does that over and over and over until it minimizes its error margin.
Hmm.
And so in the beginning of the training, you have 340 million parameters that are just random, and at the end of it you have 340 million parameters that have some sort of representation of the real world, of what it trained, not of the real world but of what it trained on. um, And so the data comes in that how good are these parameters tuned, like how good are these parameters to allow you to complete a task well, if that makes sense.
So
I actually
yeah,
I could show, maybe I should share this with you. I did a little bit of a representation on a linear and a logistic and a linear regression about how it starts and how it adjusts. You could see it on a notebook. I'll share that with you. It's really nice how to while you see it train and adjust itself.
that sounds really cool. Um, one thing I was try to figure out was that, or for folks that might think is like, is a larger model in file size mean that it's more trained or more intelligent? But what I'm hearing is that the size of the model is based on the amount of parameters because that's the amount of data it's being held within the model weights. And so all you're doing is adjusting those weights. So you're not going to, they're just numbers, right? So it's
Yeah,
not going to be bigger or smaller. I mean, there might obviously be some flux to some degree, but it's not going to be, if you did, 10 times more trained, it's going to be 10 times larger. It's really the parameter size that's going to determine its end size.
exactly. So
Well,
regardless of where the model is, whether it's good or bad, it'll have the same size. It is a constant size. But what really matters is how well, what those numbers are, these 100 340 parameters, what are they, and are they, because they, you have to think about it, is they in, that's a mathematical model, right? And so that's what matters. The file size, though, some people tell me, oh, the file size increases. The file size should not increase. The reason the file size increases is because certain programs attach metadata to the system.
mm,
And so when you train, the optimizer sometimes or attaches metadata of training states. That's what makes a bigger file. The model itself should always be constant at
mm.
whatever level you set it at.
Okay, that makes sense. So there are cases where the data gets larger, but it's not for the reasons that you think. It's because, as you're saying, there's additional data being attached as metadata, and that makes total sense there. Just continue on here with BERT. Yeah, there's obviously a bunch of variants. I didn't look at any of the variants. I just assume, like, I know I always see the word distill, so I assume that that's just a more optimized model. Like, I don't know if it's a pruned model or whatever you call it, but I just know that they're generally more performant, like 2-3 times, and they're cutting corners to do that. Not in a bad way. I mean, like they're figuring a way to make it more performant.
I haven't looked at all these either, but you have to think about of these as, so I think Roberta. Let me. They all came out later. Like Roberta came out in 2019, so a year later. You have to think of this as a natural, like, how man evolved. The evolution of man, where we,
Mm-hmm.
and you have to think of it like that, right? Every year there's new models, based on new understanding, based on new concepts, based on better optimizations, and so this is the natural evolution of it.
Mm.
Uh, yeah.
So yeah, I understand that. I guess I was just really getting hung up on the word distill because I keep seeing it, and every time I come across a distilled model, they always describe it as like 2, 3, 4 times faster, and they've done something to it. Whereas to again, I'm not sure it's pruning or they're doing some kind of optimization to the model to make it more proficient. Like for instance, Whisper has distilled Whisper, and I just keep seeing the term distill. So I guess my real question is like when you see these terms like distill, do you know what that means, or it's just that they're just putting that name there and it's suggesting that like is there a rhyme and reason to the naming across models, or there's no convention and people can attach whatever they want? Like sometimes I see models that have Omni in front of it, and are they just putting Omni in front of everything when they decide that they think Omni sounds cool, or
Yeah, I think these are researchers in labs, right, or people in different companies, and there's no real naming convention, and so they can realistically name things the way they want. We just talked about how really bidirectional is somewhat a misnomer; it should be non-directional. But
Mhm.
these, the namings, I don't attach too much to it,
Okay.
and they also want it to be really cool when you make an acronym out of it, so sometimes it is a misnomer for the acronym. uh,
Mm.
but a distilled model, so there's a lot of ways that you can optimize a model. Like you said, some of it is pruning, some of it is these teacher teacher models. AWS actually at reInvent, they now Bedrock, you can create these smaller student models, and what that allows you to do is to take this really big model and create a smaller model that is very optimized for your task. And so the idea is to um, instead of, and we talked about this in the previous system we ran, but maybe we can mention some of this. These models can be really big, right? They're fairly huge. And so what and a huge model means more latency, it means more resources, it means more cost. And so this idea of creating smaller models, uh, distilled models, in various ways, you could do this in many ways. You can prune, you can teach a student model, you can um, do different things. The idea is to reduce cost and latency and resources by doing that. And there's various ways we can do that. I can potentially put some research for you as to like the different ways that is done.
So I think what I'm seeing here is that distillation, distill, could suggest that it's this teacher knowledge transfer thing where you have a more intelligent model transferring to a more cost-effective model, but also to warn that naming conventions are not necessarily set in stone. So someone could put distill in front of it, and the means could be different. That's just a general I think a general warning that we might suggest is that everything you have to look at see what it does, regardless of its name tag, if it's
Yeah,
model name.
I
Okay.
think naming conventions are not there yet in terms of consistency across
Mm.
different teams.
Yeah, like I might create a model and then I decide that it's distillation, but I actually don't know what distillation means, and like
Distillation, I came
it
from a
appropriate.
chemistry. Yeah, I came from a chemistry background. I think the word distillation means to take the essence of, right? To
Mm.
uh, when you distill a chemical, you're really taking all of the impurities and getting the essence of that chemical.
Mhm. See,
And
I
so
would, I would, I would just make a model smaller somehow, and then I would put distill in front of it, and everyone would be like, "What are you doing, Andrew?" But I'd be like, "I don't know. I thought that's what it was." Yeah. So then I put this. While BERT is an older model, still used for ubiquitous baseline in natural language processing. That's specifically what um, Wikipedia said. So they're saying that it is, I guess, a comparative for when you're doing NLP experiments to use it as a baseline. I don't know what they mean by that. I just know that they say that. So I'm not sure how you use it as a baseline, but that's what they say.
I'm not sure. I think the biggest thing in my mind, like we said, is that it is an encoder model only. So it's great for when you have text that you want to do a very specific task on. You want to reach a particular conclusion. And that's where these encoder only models come in.
Mm-mm-mm. And so here I have an example of BERT using sentiment analysis. So here we're using the Hugging Face pipeline. We're using the BERT base uncased. And then we have a couple sentences. And then it I guess what it does here is it downloads the classifier model. I'm not sure how you like to work with models, and I'm not sure if Hugging Face is too high abstract for what you want to do day to day. But as far as I understand, what's happening here is that when you use the Hugging Face pipeline and you say sentiment analysis, even though we're specifying the BERT-based uncased model, it's going to download a version of the BERT-based uncased model that is fine-tuned for sentiment analysis. I think that's what's happening here, as that's what the documentation kind of suggests. But yeah, this is an example here of BERT, and I don't know. That's all I got. But I'm not sure if you have any thoughts on the code, or if there's anything to talk around the code for pre-training models, or sorry,
Um,
further train models. Sorry.
well, I mean, I think going back to the reInvent keynote from Werner, the idea of simplicity, like everybody wants the simplicity. Remember that was a really good talk. And this idea of abstracting for you. So I think there's a lot of all of these, like the fact that you can do this with a huge model with a few lines of code is really impressive. But what that also means is that there's a whole lot of complexity under the hood, and the way you need to deal with these is to actually understand how the system works, how the API, all of these libraries work, what this provider deals with. And so the way I like to work is to stick to a single provider, or at least like a few providers, so that you can understand kind of their way of working, and how to look at their documentation, and do all of that. Why? Because again, there is a huge amount of complexity that is kind of removed and abstracted for you, and you can just call a few lines of code. And while that sounds great, you're to really understand what is going on, you really have to peel the lid off a little bit and understand. And so if you kind of get used to particular providers, then you can understand how their documentation work, where to find particular information, where to read particular things, if that makes sense.
So that word complexity, it sounds like, it almost sounds like they're the opposite, but but the idea is like you have a complex system, but they simplify it for you, and so you understand these complex tools through this simple interface. So you are doing complex things, but things are abstracted away from you.
Exactly. Like, look at that. Is that enough? Like the amount of things that happen, like for it to understand that sentence, there's a process of tokenization. It's cutting these into tokens, and then it's embedding them, and then it is running them through a mathematical system, and then it's bringing them back to a label. So there's a whole lot happening, and you write 2 lines of code, right? It's pretty interesting.
But as the person that's using it, I should generally understand what's actually happening, like the complexity, and appreciate how much is being abstracted away from me, or the fact that there are cases where yes, this is good in this use case, but you might have to go and do this more at a lower level. Like the same thing with high level abstract languages and lower level abstract languages, is that comes flexibility, or come more complexity will get more flexibility.
Yeah.
But yeah, that's BERT. And I don't know. Do you think they named it BERT because of Sesame Street character? Like somebody had a kid, and they're like,
It's
their
very
favorite character was
possible.
BERT, and they're like, let's figure out a way to name it BERT.
It's very possible. I worked in labs for a long time, and a lot of times we did reverse engineer the name to be the acronym. So yeah, very
Okay.
possible.
So you're part of the problem, is what you're telling me.
I mean,
Okay. Well,
marketing, it has to be easy. It has to roll off the tongue. It has to, you know.
Well, I appreciate your expert input on BERT here. I definitely understand it a lot better. I hope that people that are watching, when they hear me talking, they don't realize how much information that is missing from what I'm saying. And I'm just trying to give them the most practical route, the best way I understand it. Kind of like Chef Ramsay, where sometimes he'll have videos and he'll talk about the process of something. It's totally wrong, but the outcome of what he does is correct. And so that's what we call a practitioner, someone that's good at doing someone, but doesn't necessarily know exactly how they're doing it and gives inaccurate explanations. And so folks just need to understand that as I'm making content here. And that's why I have you here, to expose the lack of knowledge I have. So I appreciate your time, and we will see Rola in more videos, and we're going to continue on with the course. Ciao, ciao.